In this video, I'm going to prove two important results, and before I do that, I want to define some notation. So let's say I have a vector field, and let's say within this vector field I draw a path starting at some point, and then it keeps on going, and then it returns back to itself. So you see this is a closed loop. And then if I want to evaluate a line integral along this loop, so let's call this path C. So if I want to evaluate this line integral, I will use this expression to represent the line integral. So the circle over here that you see tells us that this path here is a closed loop. So that's what I want to define. I want to define this symbol. So with that out of the way, I want to prove two different results. So the first thing I want to prove is that if we are given a vector field f, and we know that it is conservative, then I want to prove that if we're given this condition, then we will immediately be able to conclude that this line integral here will always be equal to 0 for any closed path C. So this closed path C here is arbitrary. So if this is conservative, if the vector field is conservative, then for any arbitrary closed path C, its line integral will be equal to 0. So that's what we want to prove. So in order to prove that, let's start off with this expression. And let's say within this vector field, let's draw out an arbitrary closed path. So let's say this closed path starts from this point A, and then along its way it reaches some point B, and then it goes back to A. So this entire closed path here will be our path C. And what I want to do now is to break up this path into two different parts. So for the segment going from A to B, I'm going to call this C1. So C1 goes from A to B. And then for the segment from B to A, I'm going to call this part C2. So what I'm doing is that I'm breaking up the entire closed loop C into C1 and C2. So by doing that, I can now write this line integral out as a sum of two other line integrals. And so this is what we have. And now I want to define another path. I want to define a path called C2 prime. And C2 prime is going to be a path that looks exactly like C2. So it's going to be a path that has the same exact shape as C2. But the only difference is that C2 will instead travel from A to B. So you can see that C2 travels from B to A, C2 prime will travel from A to B. And the line integral along C2 will actually be related to the line integral along C2 prime by a negative sign. And we know this is true because you can just write this back out in the form of a sum. Remember we defined this in the first video, and if you write it out like this, you'll see that if you reverse your path, if you reverse the direction of your path, all you're doing is reversing these vectors over here. So the only change will be an extra negative sign at the front. So since I'm going from B to A for C2, and now I'm going from A to B for C2 prime, these two line integrals will be related to each other by a negative sign, because all we're doing is just flipping these vectors over here by a negative sign. And so with that said, now we can rewrite this expression over here as being equal to the line integral along C1. And instead of writing the line integral along C2, I'm going to write minus the line integral along C2 prime. And now you see that C1 is a line integral from point A to point B. C2 prime is another line integral from point A to point B. And we're already given that the vector field f is conservative. So C1 and C2 prime are both line integrals with the same starting and ending point. And as we know from the definition of a conservative field, we know that these two line integrals here will have the same value. So if you minus a number by itself, all you're going to get is 0. And so there we have it. We've proved that if your vector field f is conservative, then the line integral along any closed path will be equal to 0. So this is what we've proved. So the second statement that we want to prove is the exact reverse of what we just proved. Now we want to prove that if we're given a vector field with the special property where every given closed path will have a line integral that's equal to 0, then this immediately implies that the vector field f is conservative. So this is what we're going to prove now. So in order to prove a vector field is conservative, we need to prove that for any given 2 points, A to B, we can specify paths that lead from A to B, and we need to prove that the line integrals along these paths are path independent. That means it doesn't matter what path we choose as long as they have the starting point A and an ending point B, then any line integral evaluated along these paths which connect A to B will give you the same result. So let's say this path over here is C1, so this path leading from A to B is C1, and then let's say this other path, this other arbitrary path also leading from A to B, let's call this C2 prime just to be consistent with what we defined before. So let's say this is C2 prime. Then if we want to prove that the vector field f is conservative, then we need to show that the line integral along C1 will give you the same result as the line integral along C2 prime. So right now all we know is that any closed path within this vector field will have a line integral that's equal to 0. So we're going to use this fact to prove that the line integrals along C1 will indeed be equal to the line integral along C2 prime. So this is what we're going to try to prove. So in order to prove this statement over here, we're going to have to first define another path, and then we'll call this path C2. And C2 will be a path that has the exact same shape as C2 prime, but it's going to be a path that goes from B to A. So C2 prime goes from A to B. C2 now is a path that goes from B to A, and both of these paths will have the same exact shape. And as I've stated before, the line integrals along these two paths will be related to each other by a negative sign. And the reason why I've defined this is because now given this path C2 over here, if we consider this sum over here, the sum of the line integral along C1 and the line integral along C2, you'll see that this sum over here really just leads to a closed path. So C1 is this path over here that goes from A to B, and the C2 is this path that goes back from B to A. You'll see that the line integral along C1 plus the line integral along C2 is really just a closed path. So this whole expression here is just a closed path. And then as we know, within this vector field, we're already given that any closed path will have a line integral that's equal to 0. So we know that this sum over here is equal to 0. And then we also know that this line integral over here is related to the line integral along C2 prime by a negative sign. So we know that this line integral is equal to this expression here. So I'm just going to replace this by minusing the line integral along C2 prime. And we know that this is equal to 0. And so this immediately implies that the line integral along C1 is equal to the line integral along C2 prime. And so there we have it. This is the exact statement that we wanted to prove. So this proves that if our vector field has a special property where every single closed path has a line integral equal to 0, this immediately implies that line integrals with the same starting and ending point will have the same value as we've just shown now. And so this pretty much proves this statement over here.